Angela, can you take your test? Yours is where? All right, ladies and gentlemen, you should have out your notebook and your Unit 6 packet, please. All right, so before we start the practice questions on page 1 of your packet, I just want to finish that little story that I ended with yesterday about what's going to happen if you are not wearing your seatbelt and you don't have an airbag. So I was telling you about my cousin, Jonathan, who that happened to and was taken out of his car with the jaws of life. Helicopter down to Albany Med. They took out the top part of his skull, medical-induced coma until the swelling was reduced. 6 months later, and when he finally started to wake up, they realized he didn't know how to talk anymore. He didn't know how to eat with a fork, didn't know how to go to the bathroom, couldn't walk, couldn't add 2 + 2 again. It was like an infant starting all over again. And so when he finally was discharged from Albany Med, he was transferred to Sunnyview Rehabilitation Hospital in Schenectady to learn how to do as much as he could. But the problem is, when you have a traumatic brain injury like that, your brain doesn't always recover 100%. So he has grand mal seizures almost daily, even though he's on some very high dose medications. But if you were to talk to him, and he survived it, but if you were to talk to him, he's 42 now, you would think you were talking to a 5-year-old. That's about as much as his brain was able to recover from that. And because of the seizures and the brain injuries he sustained, he will never be able to hold a job. He can't work. He's 42. He's on disability, which means he also needs round-the-clock care. He's got to live with somebody. So he's living with my mom's sister right now, my Aunt Jackie. She's 76. She is not going to live forever. He will probably outlive her, as most kids usually outlive their parents. And after she passes, where is he going to go? Probably into a group home or some kind of a facility where he can spend the rest of his days. It's been a very difficult situation, obviously, for him and his family. He will never be able to go to college or do those things. So it's just a tragic thing where if you make a bad decision, that can affect your life like that. And that's what happened for him. So I tell you that, the personal piece of it, because, yeah, we're talking about an object in motion stays in motion. Okay, great. But sometimes you think you're invincible as a young person, and by making a bad decision, you find out very quickly that you're not. He very easily could have died from that, and he didn't. And there was a student here, I think it was my 3rd year teaching here, my 3rd or 4th year. I was teaching in the classroom across the hall, and I had a 16-year-old student named John who was driving I think it was a Friday evening. His girlfriend, Tanya, was in the passenger seat. He was wearing his seatbelt. She was not. And he was going too fast here on Raider Boulevard, making the turn around by the football field near the mug. Okay. And he lost control of his car, going too fast around that turn, and went into they had concrete pylons that were coming up out of the ground. He went headfirst into that. Because he was wearing his seatbelt, he did not get ejected from the car. His car was totaled, but she did. And she passed away. Now imagine, he was a junior here at the high school. Can you imagine what he lives with every day after that? Can you imagine being responsible for killing your girlfriend? Yeah. Yeah. Okay. So that was a student's funeral. She was not in my class. She was in taking physics in the other classroom next door to here. I used to teach across the hall, and it was awful. It was awful for everyone. But I know he probably still carries that guilt, even though he's now in his late 30s. I mean, that was 24 years ago. So just something to think about when you are driving. You have an awesome responsibility. And as much as you pray that you can break the laws of physics, I'm here to tell you you cannot. Physics will catch up to you, and you want to be safe about what you're doing. So just be responsible drivers. Okay, that's what I'm telling you. You've got to be as responsible as you can. And it's not always about looking out for you. You have to look out for other people too, doing stupid things as they're driving and not paying attention to what they're doing. So just be careful of that. I don't want to go to your funeral. Okay. When I'm 90 years old and you see that I've passed, and you can come to my funeral. Okay. But not the other way around. It's an awful thing. It's a really awful thing. So on that somber note, let's go through the questions in your packet. But I do want you to have your notebook out, because you may need to look up some things from yesterday's lesson on Newton's first law, okay, in case you don't recall. So let's have out your notebook with your notes from Newton's first law in front of you. And your packet, we're going to start right at the beginning of the packet. We have to get through the questions on pages 1 and 2. Your homework for Monday is page 3. And depending on how quickly we work through these questions on pages 1 and 2, you may get the opportunity to get all of page 3 done before you leave here today, which would be very nice. That way you just have to look at your notes a few times over the break. Okay? All right. So let's talk about question 1, which says, imagine that we are in a place in the cosmos far, far from all gravitational and frictional influences. This is a fictitious place, by the way. Suppose that an astronaut in that place throws a rock. What is the rock going to do? Is it going to gradually stop or continue moving in the same direction at a constant speed? Which one is it, Liam?
Continue motion in the same direction.
Yeah, so you said B. That is correct. Now let's talk about why that is. According to Newton's first law, an object in motion will continue moving at a constant speed in a straight line unless what? Why wouldn't you move with a constant speed in a straight line? What's the end part of Newton's first law?
Unless it's acted upon by unbalanced.
That's right. Unless there is an unbalanced force. And the fact that it says there's no gravity or friction, that's telling you there is no unbalanced force. So since there's no unbalanced force, because you're moving, you got to keep moving at a constant speed in a straight line. Or not you, but in this case, the rock. The rock would keep moving at a constant speed in a straight line. Okay, any questions on number 1? All right, let's look at number 2. And I have to define something in number 2 for you. Number 2 says we have a 2-kilogram object moving horizontally with a speed of 4 meters per second. I want to know how much net force is required to keep the object moving at that speed in this direction. Net force is a synonym for unbalanced force. So I could either say net force or I could say unbalanced force. Either way. One other thing, go to your reference table, page 6. You'll see that symbol F net for the net force. You can check that off. Again, this just refers to the unbalanced force that's acting. And this is also going to be measured in newtons because it's a force. So F subscript net refers to the amount of net force or unbalanced force. How much force is unbalanced is what we mean by net force. So here I'm asking you how much unbalanced force you need in order to keep it moving at a constant speed in a straight line. That's what that means. Constant speed, straight line. What does Newton's first law say about the amount of unbalanced force to make that happen? You can even read it with what we wrote in our answer to number 1. An object in motion will continue moving at a constant speed in a straight line unless there's an unbalanced force. So how much unbalanced force do you need to move at a constant speed in a straight line? None. That means the net force has a value of 0 newtons. Again, this is Newton's first law. Because there isn't an unbalanced force, you just keep moving at a constant speed in a straight line. This was asking you how much force had to be unbalanced. None. You don't want it to be unbalanced. You want it balanced. This is all about having a balanced force. Okay, number 3. Mac and Tosh are arguing in the cafeteria. Mac says that if he flings the Jell-O with a greater speed, it will have a greater inertia. Tosh argues that inertia does not depend on speed, but rather on mass. Who do you agree with and why? And please do not do this at home. And please do not do this in the cafeteria here at school either. Don't tell them that you're doing a physics experiment. Okay, they're going to be like, what? Get out of here. Clean it up. So, who's correct? Think about that term inertia that we learned about yesterday. Tosh is correct. Why? That's right. So Tosh is correct because inertia is measured by mass only. By mass only. Speed has nothing to do with it. And remember what inertia is. Inertia is defined as your resistance to a change in motion. Okay, that's what we mean by inertia. Inertia is resistance to change in motion, and you can figure out how much inertia you have by looking at your mass. Speaking of mass, I hand this around again, right? Every day for a few days. So what is this? How much is this? Remember? A kilogram. That's right, because we need to know what a kilogram is here in the metric system. Okay, number 4. If you were in space in a weightless environment, would it require a force to set something in motion? So you've got this pencil in space. It's just, let's just say it's floating there. You want to make it move. Do you need a force to make it move? Yeah, it doesn't matter. Newton's first law applies no matter where you are. So yes, an unbalanced force is required to change an object's motion. And when we say we're changing the motion, we're going from rest to movement. That is a change in motion. If you're starting off at rest and now you're going to move, something's got to push it to make that happen. Okay, number 5. John Madden spends most Sunday afternoons at rest on the sofa, watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? By the way, John Madden, you know who he is? Yeah, okay. So you want to tell everybody who he is? That's correct. But who is John Madden? Tell the class who he is.
So, it's like, well, the video game Madden is kind of.
Okay, and I don't know that video game.
It's
Really?
It's a football game.
Okay. Okay, so John Madden is I think he's deceased now. He was, when he was alive, he was a professional football announcer for ABC Sports. That's who he so every Sunday afternoon while he was alive before he retired, he was commentating on the games and so forth for ABC Sports. And he was a large man. Okay, so this is hence the question. What is resting on the sofa watching pro football and consuming large quantities of food going to do to his inertia? It's going to increase. Why? Yeah, that's right. Yeah. This should happen to all of us over Thanksgiving, right? Okay. Increase because his mass increases. Yeah. And it says don't do this at home. Okay, you get a pass for Thanksgiving. Come on.
If like figuratively, think about it. Isn't doing anything for a long period of time going to increase your nutritional mass to change it?
Not necessarily, no.
If you exercise for a long time, is it going to increase your
Well, that's the thing is, no, if you're going to exercise for a long time, then you're going to resist not exercising because that's a habit.
No, I
Not necessarily.
I just more like a philosophical kind of.
Oh, philosophically, yes.
run every day, but
All right, let's look at number 6. Ben Too Close is being chased through the woods by a bull moose. Why is he being chased through the woods by a bull moose? He got too close. That's right. Okay. He was attempting to photograph this bull moose. Now, the enormous mass of a bull moose is extremely intimidating. Yet, if Ben makes a zigzag pattern through the woods, he's able to use the large mass of the moose to his own advantage. Explain that in terms of inertia and Newton's first law. If you were ever to come in contact with a bull moose, you would be very intimidated because they're probably like 8 to 9 feet tall. They're huge. Huge. That's not going to help. You need to zigzag in order to escape the bull moose. Or let's say you're camping and a bear is there. You're going to do the same thing. Zigzag. Why? 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 Caroline. Yeah, or change direction because all they're going to do is they're going to try to follow you, zigzagging. They're not going to be thinking, oh, I'll just go straight and catch them. Okay, they're animals. They're not going to do that. They are just going to chase you, zigzagging. It is hard for them to zig and zag when they are much larger than you are because they have more inertia. They have more mass. So the moose has more mass and more inertia than Ben. So the moose has more resistance to change in direction, which makes the moose need more force. So Ben escapes. Woohoo! Yes.
How come like when you see like little animals run, they look like quick, like they look fast. But when you see like an elephant run, like an elephant's faster, but like they look slow.
It's relative to the ground around them. And they're just going straight.
Oh yeah.
It's like proportional.
Okay, number 7. 2 bricks are resting on the edge of the table. Shirley, she's short, stands on her toes and spots the two bricks. Why does she have to stand on her toes? Because she's short. Okay. She acquires an intense desire to know which of the two bricks are most massive. Since Shirley is vertically challenged, she is unable to reach high enough to lift those bricks. She can, however, reach high enough to give them a push. Discuss how the process of pushing the bricks allows Shirley to determine which of the two bricks is more massive. And what differences will she observe? And how can that observation lead to the necessary conclusion? What do you think? Manure? Yes, that's it exactly. Very good. So the more massive brick has more inertia and requires more force to move. That's it. Numero 8. The Colony High physics teachers are taking some time off for a little putt-putt golf. The 15th hole at the hole-in-one putt-putt golf course has a large metal rim which putters must use to guide their ball toward the hole. Miss Famoso is guiding a golf ball around the metal rim. And when the ball leaves the rim here, which path is the golf ball going to follow? So the ball starts here and it continues around like this till it gets there. I want to know, what is it going to do when it leaves right here? Now, just to visualize what we're talking about, I can kind of make a little rim like we have there, kind of like this. So if the ball started here, came around, got here, which way would it go? That's what I want to know. Is it going to go towards 1, 2, or 3? 2. Why?
Until it gets acted upon by
Yes.
Okay, and after it leaves, is there an unbalanced force on it? There's nothing pushing it once it leaves. Okay, so let's answer that, and then we'll make sure. Actually, let's make sure you're right first. We'll try it out. Okay. It did, right? Did you see it?
Yeah.
And wasn't it moving in a straight line at a constant speed?
Yeah.
Exactly what we said it should do. Newton's first law. All right, so it's going to go towards 2 because once the ball leaves, there isn't an unbalanced force. So the ball must continue in a straight line with a constant speed. And as we just said, that is Newton's first law. Now, it's not okay to just tell me it's path 2. You have to be able to explain these things, right? That's part of your learning objectives. Can you explain what's happening? Why is it happening? All right, number 9, last one. We have a 4.0 kilogram object moving across a friction-free surface with a constant velocity of 2 meters per second. Which one of the following horizontal forces is necessary to maintain that state of motion? Okay, if you are maintaining that state of motion, what is the acceleration of the object? 0. According to Newton's first law, how much force do you need if you are not accelerating? 0. Choice A. This is Newton's first law. That's it. If you want to not accelerate, you need no net force or no unbalanced force. Okay? Questions? So what's your homework for Monday? Page 3. Go ahead and work on that page now, please.